started. Welcome to another Thursday Swarm Lab seminar. Hopefully everybody got something to eat. Today we're very fortunate to have one of our very own, Adam Wolisz, is here. Let me give you a brief rundown on Adam's bio for those of you who don't know him. Adam received his degrees diploma in 1972, PhD in 76, and his abilitand in 1983 from Silesian University of Technology, Gliwice, Poland. He was with the Polish Academy of Sciences from 72 to 1990, and GMD Focus Berlin from 1990 to 93, and part-time from 95 to 2005. He joined the Technical University in Berlin in 1993, where he is a chaired professor in telecommunication networks, leading the Telecommunications Networks Group, and executive director for the Institute of Telecommunication Systems. I don't think I can say that word one more time. He's also an adjunct professor at the Department of Electrical Engineering and Computer Sciences at UC Berkeley. His research interests are in architectures and protocols of communication networks, and recently he's been focusing mainly on wireless mobile networking, sensor networks, and the Swarm Lab. Thank you, Adam.
Thank you very much for the invitation, for the opportunity to give the talk, and for the introduction. By the way, if you'd like to see some more details specifically as for the wireless networking, so I'll be giving a talk next Friday, the 22nd in BWRC. So there'll be kind of like complement to what I'll be talking about today. Well, greetings from Berlin. You know, we have a lot of space. The university is in the downtown, but also in the green area. So you are welcome to visit us someday. What I would like to talk about is essentially a couple of issues. I would like to start very shortly with the notion of context in traditional usage. Then I would like to give some facts about network traffic development nowadays, and then focus mainly on this last bullet, namely using context to improve data delivery. And I'll give examples mostly from our research, partially jointly with people from BWRC, mostly from my group in Berlin, and obviously that is a work sponsored by several projects and resulting from the interaction both with Berlin and with people in BWRC here in Berkeley. So the notion of context, it pops up in different areas. I have picked up something which came around 10 years, 15 years ago in the space of ubiquitous computing, which has a direct relation to the swarm issue. And one broadly accepted definition from people from Georgia Tech says that context is any information that can be used to characterize the situation of an entity. An entity is a person, place, object that is considered relevant to the interaction between user and application, and that is the key issue, including the user and application themselves. So whatever gives us information about the environment to help in organizing the best interaction between user and application, and the background has been the application should possibly in the best way support the user, his needs, his information interest, that is relevant, that is the context. Now, what I would like to stress here, that obviously the interaction between the user and the application needs some communication, you have to use that, but here in this view, the communication is kind of in the background. The foreground is user-application relation, which happens somehow. Now, let us see what happens with communication nowadays, where the ideas of application supporting people everywhere, supporting people continuously, are reality. We have the smartphones, we have the tablets, which are exactly for this purpose. There are some numbers about the deployment, so that booms, that is the majority of devices sold nowadays, and that changes completely the communication style. That is something we have to keep in mind. Namely, previously, over years, we used workstations, we used laptops, which occasionally have been connected. Now, those devices essentially are following a different modus of operation. The modus stay always connected, stay always online, communicate continuously, keep information in the cloud, shift the information back and forth. Result, increase of the traffic. So the actual, very widely cited, I'll show that in the next picture again, a Cisco mobile prediction of the traffic says, okay, we will have something like 16-fold increase of data traffic per single device between 2010 and 2015. And that results with this picture, which everybody in each talk will show you, how the traffic is predicted to grow. It's mobile traffic, by the way. And that really is kind of beautiful and, for me, kind of scaring. Why? Well, because it doesn't come for free. You have to invest in the infrastructure. And I've just picked lately a couple of numbers. So Vodafone Australia is throwing 1 billion. AT&T in 2012 has been throwing 20 billions in wired and wireless network extension, installing hundreds of distributed antenna systems, thousands of new antennas. Now, everybody, even small companies, everybody is putting money there. Okay, where does the money come from? Well, it's interesting. That's another more aggressive even prediction of traffic growth coming from Korea, which is leading in the deployment of the mobile applications. Interesting enough is the observation, which by the way confirms, or is confirmed also in the market here in US, that average revenue per user does not increase as quickly as overall data traffic per user, meaning that the providers have to deliver bigger and bigger amounts of data for less and less money. So there is a problem. And they have to invest. So they have to put a lot of money to building up the infrastructure. The revenues are decreasing. So we have a problem. There's a fundamental issue. And this fundamental issue means that the only solution for that is increase of efficiency of data delivery. And what I am advocating is a point of view that we have completely to change the mindset when talking about transport of data. Namely, we have to keep in mind all the time that the user is interested in services, not in volume of data. The traffic growth is not what providers should keep looking for. They, for a very long time, they have been happy to double the minutes in the telephone networks. Wrong. Not for data. They should not be happy if the traffic grows. Now, the goal, the utmost goal is to keep the user satisfied with as small amount of data to be transmitted as possible, as first goal. And the second goal, the data which really has to be transported should be transported as efficiently as possible, meaning using as few resources as possible. And I'll give a little bit later one possible metric for how we could express the usage of the resources. I have elaborated that in a pretty recent paper, so if somebody is interested, can look into that. In other words, we have to start thinking in different terms. So far, we said, in the classical, say, ubiquitous computing world, we wanted to have the context in order to enhance the application. Now, here, we have to start speaking differently. We need to do sensing to recognize the context, but use the context also for more efficient communication. So it's not now the communication supporting transmission of the context to the application for the sake of better tuning of the application, but that's using of the context, whatever it might be, to improve the communication, to resolve the paradox of explosion of data growth without revenue following that. And I'll give some examples that we elaborated with John Wozniak 2 years ago, after several discussions. And then a couple of examples how you could achieve that, the reduction of data. So watching video TV is the most common press sleep activity. worldwide. Now, people fall to sleep, the video is running further. As long as it's classical broadcast, nobody cares. You broadcast. Well, you pay some energy cost, not so bad. You start doing it over internet, you start doing streaming over internet, it's traffic. And if you look back to the Cisco prediction, that's exactly video, which is the biggest part of the story, the mobile video. So you see, that is an issue, just exemplified by that. How can you change that? Very easy. You take a sensor, there's something which you can buy for around 70, 80 bucks, which, by the way, can do recognition of whether you fall to sleep or not, and could do a lot of other nice things, like following your fitness, taking your pulse measurement, blood pressure, whatever. So you invest 80 bucks, you are more healthy, your life might improve in quality, and you can avoid this effect. You can shut down simply the flow of data if you don't need it. Now, we could go in more complex situation. Staying with the video, because that's a nice motivation. So many people enter their home, and first action is again switch on a TV set and start learning. Again, IPTV, again, traffic. Now, usually you'll go to the kitchen, start cooking your pasta or whatever, you ignore the video. So either you look from far, and just a little bit of shadow is interesting, probably the voice is interesting, the high-resolution video is of no reason to follow. So that gives a motivation, one of the motivation, to consider whether we are able to sense human interest in some objects. And I'll give you an example, which we followed in our lab, of trying to discover the interest in some object. So look here in this setting. I'll show you in a moment a small video illustrating that. So in this setting, that's kind of like exhibition hall. That's foyer of our building. And we have put some objects here. There are plants, could be sculptures, whatever. And we would like to know if there are several people in the space who is interested, say, in this bottle, and how can I discover that? So we took a criterion of discovery, who is interested in that, coming close and stopping in front. Very simple criteria. Now, how would we like to recognize that? We said we can fuse two types of information. We fuse the information from one single camera in the room, which does not recognize people. Recognizing faces is obviously possible, but it's computation intensive, and it's not so trivial. So we say, okay, we are not interested in that. We would like to do something much simpler. What we do much simpler, using open source, OpenCV library, it's very easy to recognize shape of a human. You don't know who it is, you know it's shape of the human. Now, we are leading this shape, following the shape of the human with our processing, and we assume that this human being has a sensor with accelerator. It could be a smartphone, say in his pocket. And then what we do, we correlate the movements got from the following the shape of the person with the reading of the accelerometer, and that's exactly what you have. The red one is from the video analysis. The green one is from the accelerometer. Now, if you have several people moving here and several of those shapes, you can correlate the two readings, one from the video and one from the accelerometer, and you can pretty nicely tell which smartphone belongs to which shape. Then, obviously, accelerometer will give you the pose that you stop in front of that. The video can easily give you proximity to the object, and in that way you can very nicely identify which carrier of which, say, smartphone is exactly in front of each object. There are some details about experiments which we have done, and some data about the speed of recognition. And essentially what I would like to do, I would like to show you a short video. However, to be honest, that is not done in real time. That was collection of data and post-processing. So just to be completely frank in the research community. So here we go. That is the whole. And then a single person is coming, is recognized as shape of the human, is followed, is coming close to the object. Then we do the computations, and yes, the interest has been recognized. So we know, we did the correlation, we know that is this carrier of this phone who is interested in that object. And the same story can be repeated in relation to other objects. As she comes closer to that, it's interest detection. The same with the third object, that is interest detection. And in the, in the next few seconds, I'll show you the same story with several people, where we can very nicely tell who is interested in which object, and the resolution was pretty good. So in our experimental setups, we could distinguish people as close as like half a meter without a problem, and say who is interested in what, and tell that very precisely. So you see that is exactly a kind of grouping of people, and we are recognizing that for each and everybody. So that's so far this video. And let me come now back to the story, because I think the story has a couple of interesting takes. Namely, now that are the data about frequency, whatever, whoever is interested in technical details. But philosophically, why we believe that this approach is interesting, and how does it differ from what we have now in the museum, where you can just lend a gadget and come close to some device and to some object, and that will start talking. So the difference is that if you take an anonymous piece of equipment in the museum, it's not personalized. Here, I am correlating that with, say, your smartphone, which can have your profile. So if there will be visitors, say, in the Museum of Technology, obviously the level of interest of Chris will be different than the level of interest and knowledge from of a faculty in School of Law. So I can personalize the information rather than broadcast whatever might be relevant and overflow. Okay, now another my classical example, which I like very much, and that will be the last in the series of reduction of the amount of information, then we'll come to efficiency, is a baby phone. Well, almost everybody knows what is a baby phone. Classically, that used to be a phone, and you had a kind of second gadget taken with you. One was close to the baby. The baby, you could listen the noise produced by the baby. Now, how can you improve a baby phone? Well, you could do a video baby phone. You could do a high-definition video baby phone and hi-fi high-resolution video baby phone, and the bandwidth will be bigger and bigger, but the comfort for the user, well, will be relatively, well, you will be better informed. Now, why not go completely differently and say you have intelligence, you process the signals from the microphone, you process the signal from the camera, and you send a few bits. Baby is sleeping, baby is awake, And yes, you have a push button. If you would like to look at the baby, you can do it, but only when you really need it. By the way, funny enough, I think a year ago, such application for iPhones popped up, but very recently. So that is just the trend where the story should go. That was the first step. How can we reduce the amount of information? Just some examples. But I believe I could convince you that there is a lot of potential. We can do a lot. Now, there will remain a lot of information which we would like to transmit. And then is the question, how can we do it really efficiently? And now I would like to spend the rest of the talk addressing some examples of improving the efficiency of delivery given we have an amount of data to deliver. So first of all, if you are speaking about efficiency, we have to start thinking, how do we measure the efficiency? What is the metric of the efficiency? So obviously, just amount of bits is nothing. You have the amount of bits which have to be transmitted. They might be categorized in different services, but essentially what we are interested in is ideally unit of service. Unit of service saying download of a book, download of a video, in these categories. Now, what could be candidates for the metric of efficiency for such a service for download of a book or download of a video? I believe that for wireless communication, a pretty reasonable candidate is the what I call area of interference, which is kind of product of time in which a given bandwidth is blocking some space from reusage. So if you have, imagine simplest case of time division multiplexing, that would mean you have a time, you have the bandwidth, and you have the coverage where you cause strong interference to others, effectively prohibiting the usage. Obviously, it's technology dependent. If you are able to do signal cancellation and reusage, there will be a different scope of the surface. So the numbers are technology dependent, but I think that such a product gives a pretty reasonable first approach how one could start reasoning about the efficiency. So obviously you would like to keep this footprint as small as possible while delivering the proper service. So how can we do that? One way which is now very popular, very broadly discussed, not new by any means, no new, but very now popular, is heterogeneous networks, HETnets, exploiting the fact that we have a huge amount of different technologies which differ in many features, but among others in the spatial footprint, in the coverage, in the sense of space. And that opens a lot of options to play this out. I'll mention some recent work, not from our group, which uses time flexibility combined with the fact that smaller footprint is more efficient. So you try to go into smaller technologies with possibly smaller footprint. And you might use time flexibility, which is, if you like, analogy to the electricity demand shifting, which has been discussed here since many, many years and implemented. So, do you really have to be just at the moment which you need? That is a very interesting story. A very interesting study a couple of years ago related to planning to route download. The classical way is you run with your smartphone, it follows you, you have the actual maps, and you have this kind of system which supports you in getting your route. Now, mostly you know where you will be going next day. So what they did, they worked with real people and encouraged the people to trigger a pre-download of all the maps and all the information in the previous evening. Doing that at home, using the short distance links, You could do wireless LAN, you could do ultra-wideband, even shorter, even smaller footprint and quicker. And then you have everything. Now, interestingly enough, obviously the efficiency is incomparable, but also the stress factor for the users was much better. They preferred the preloading. They didn't suffer because there was not good coverage and because they had to decide do I turn right or left, and I'm not up to date because something went wrong. Now, funny enough, there is another estimate from Infocom 2011 saying that if people use Flickr for upload of their content, then essentially a huge amount of the content is uploaded with a delay up to 10 hours. So there might be cases where you really go with the camera to a shop and you would like to show your husband or wife, look here, that's the couch, should I be interested, should I grab it? But it's not so every day. Most of the stories you post-process, you upload later, it's not immediate. So again, you can select a technology and you can do that. The question is, how much better could we do that having coupled not with user decision like here, but with a context recognition in the sense, well, we have a very good prediction of future. It's our calendar. More and more people have electronic calendars. They put their schedules. It's very easy to grab that and know what to expect. Obviously, you will have wrong hits, false hits, no doubt about that. But boy, if the economy of download is so huge, take 20% overhead, who cares? Okay. Just side effect is locality of storage. I mean, I'm not saying that we should give up the backup in the cloud and all the benefits from the cloud. But essentially, if you look at our today style of operation, we don't put increments. Just somebody here, I think, 3 or 4 weeks ago mentioned the email where you attach all the previous information and send it back and forth. It's growing and growing and growing every time. And you are shifting bits which are completely meaningless because they are already 55 times on the other side. Hundreds of further examples. So the thesis is, now the storage becomes cheaper. We can afford to rethink differently the split between communication and storage, caching essentially, and think about how few information do we really need to transport versus keeping the copies only synchronized by the increments as much as it is necessary. By the way, when I speak about storage, it does not mean that we have to carry a device, a big laptop, whatever. The storage could be in our skirts, in our shoes, wherever. That's not an issue at the moment. So this trade-off should be reconsidered. And now I'll give you some examples from every day. So today, the most popular way to try to achieve this economy, which is really used by the providers, is the WLAN offloading of cellular traffic. They started doing that pretty recently after several years where they claimed wireless LAN is the biggest enemy because he's taking traffic away from them. Authentic statements. Okay, but it's not so easy today. Go to the downtown of Berkeley, you'll see tens of access points, and you'll be not able to use most of them. You don't have the access right, and that's completely inefficient. Now, even if you have somewhere a coverage, you have only coverage from specific access points for which you have the access right, and there might be different access points much closer to you, which would serve you with much greater efficiency. We'll talk about that later. There are not technological obstacles. They are mostly legal obstacles. that's security, and there's lack of incentives to do that, and lack of understanding that the incentive might be the benefit of all the providers in increasing the capacity if there will be free roaming between them. By the way, there's a lot of discussion about femtocells, the microcells for cellular networks which are starting being deployed. And again, there is this big clinch, open or closed femtocells, and mostly deployed today are closed femtocells, where only the owner of the femtocell and his visitors are allowed to use that, not the open public. It's completely breaking the rules of efficiency. Now, what we could do is, and that is the idea of the offloading at the end of the day, is kind of dynamic kicking users from one technology to another. Not letting users select it, but say, okay, depending on the load, depending on the efficiency of delivery, I could shift the user, say, to a wireless LAN and between the wireless LAN and cellular. I'm stressing the word shift because there's a lot of misunderstandings. The usual approach is you have a WLAN, you go to the WLAN, it's for free, you avoid cellular. It's not correct. The cost in the metric which I mentioned previously, incurred by a single user in a wireless LAN technology, depends a lot from the quality of the signal between the access point and the user. You are on the edge of the, say, conceptual cell of the coverage of the access point, means you go down adaptively with your modulation and coding, meaning sending of the same number of bits takes much longer, and that, by the way, creates a much higher resource usage as seen from the access point. You cannot serve other users. Also, the type of traffic matters. Wireless LANs are random access technology. They don't like short packets. You have like voice over IP on the edge of the cell. Goodbye, sir. You better kick the guy over to cellular, even better to second generation cellular, which people start thinking about nowadays, which is specifically circuit switching for voice. And it will be much more efficient, and you can use the wireless LAN bandwidth for better application. We have looked in a series of papers, we have looked in different details just to give you the feeling about some complexity of the story. I've mentioned the change of modulation and coding dependent on the signal strength. Well, while the standards give a framework for that, they don't give the algorithms that are free, they are competitive. So each manufacturer of the device has some different algorithms. In the literature, there are probably 60 or 80 already considered. And by the way, from release to release, this algorithm can change. Now that it matters, we have here done measurements on some real products with different rate adaptation algorithms, which are popular. And that is the distribution. Here you have different positions, and here you have distribution on this axis of data rate on the same position as seen by one and another of these adaptation algorithms. And you see the differences are pretty strong. Now, the problem is that the access point has no clue which kind of algorithm your laptop or device is using. So in a recent work, which will be presented next month at the Infocom, we used machine learning models to take short observation of the behavior of a device in a static position, in this case, and predict the statistics of different bit rates which will be used, different level of coding and modulation, and compared that then with the real development in the future, we can predict it pretty reasonably, so we have some better chance to say what will be the cost of serving of this device with this type of traffic due to the type of adaptation algorithm the guy has. Now, if we have devices with multiple interfaces, that's not only the possibility to shift the device from, say, Wlan to the cellular or back and forth, we could use both of them in a more flexible way. So what we did here in another experiment, we looked at a client that was a laptop using video download with modern scalable codecs with two layers, the basic layer and the add-on layer. And then we considered different options. We have been monitoring the bandwidth on a Wi-Fi and on a UMTS link available for the client. And we could do a selection. We could either decide to drop the add-on, the enhancement layer, remaining with basic quality, or shift one of the layers to the other technology, and whatever. I'll not discuss the details how we measured the bandwidth. That is just illustration of the result, just a snapshot of the result for three cases, where here we try to push over WLAN, the cheap technology, the technology of choice, both the layers, in spite of background traffic on the WLAN caused by other users, and that is a nightmare. Now, dropping one of the layers is better because it reduces the load, and if we shift the enhancement layer into the other technology, we have a very brilliant quality of the picture. So we can do a lot context-based, and obviously we don't waste bandwidth, because in this case, that's wasting bandwidth. So we have losses, we push a lot, we block a lot, the result is pretty wrong. By the way, I'll not comment on that. Another story which is relevant to some of the swarm scenarios, which we are now working on, this ongoing work is just moving the flow of data among different terminals. So imagine I'm leaving the room, and then I can discover that I'm going out of reach of this screen, so the video might be pushed on my smartphone or whatever device I carry with me, and we have the protocol under development now. Now, the other option to increase the efficiency in huge scale is direct communication. So if we go over some infrastructure, we at least have the factor of 2, which we lose always. We go up to the base station, we go down to the other user, possibly worse than that, depending on the technology. Now, we know, all of us, this terrible phenomenon that if I would like to send my presentation to John, I'll do that per email via Berlin, via IEEE server in Michigan, and back here to Berkeley, albeit we essentially could communicate using our hands, and the stick would be obviously the much higher bandwidth. So, okay. Now, the problem here, there are a couple of problems. Obviously, there are issues of security, which might be better or worse if you use the locality. I'll not discuss that. But the problem is that we have the issue of discovery, and that is killing the story. So I'm close to my device is close to his device, but the devices, besides if they are apples and we are in the same group, they don't have really a technology, not cross-manufacture, not cross-platform, to recognize each other. So we have looked at different scenarios of the discovery, and specifically, one of the recent works, which is already available to download from the journal site, was related to body area networks. So imagine you have a 802.15.4 body area network, and I'm carrying a body area network, and whoever is carrying a body area network, and we come into proximity of each other, and due to the desire to create a more complex context, we would like to exchange some data. So I can be on one of the 16 channels, you can be on one of the 16 channels, I can have some unknown to you beacon frequency, you have some beacon frequency. It's pretty nightmare how we should find each other with low energy costs. So what we looked here at are optimized algorithms for the search, organization of the very specific organization of the search, improving the story. Now, last part of the talk and last video, a couple of minutes, I would like to devote the issue of interference, because one of the aspects which critically influence the inefficiency of transmission is the issue of interference. And essentially, imagine we have just a Wi-Fi. It's deployed somehow reasonably. People try to plan it. They try to use not overlapping channels mostly. That's how the network here is built. But then comes something more. You start coming up with, say, sensor networks, which would like to communicate. And in addition to that, laptops and other devices pop up, which are not planned. People walk in and start using them. So the whole story starts changing. Essentially, that is related to the connectivity brokerage concept, which we worked on since many years with Jan and his students, which gives a framework how we could try to operate, to optimize, to get the information, to manage the information about the operation, about the environment, and optimize the usage of the environment. What I'll be talking about here are results and test beds from the European project crew, which we participate in, which took over the connectivity brokerage idea. By the way, some members of this team have been contributing to this international activity. And, well, that's kind of set of equipment which we use. I will not comment on that at the moment. And what we use is we have in our building a setup which we originally created as testbed for sensor networks. So it's like 200 nodes in regular spacing in the building, covering the building, and we have a fleet of mobile robots. The Roomba robots with Kinect on them, which we use as moving agents in the space. Now, the story is that albeit the testbed has been constructed first for investigation of operating systems, that was the cooperation with David Kaller Group in TinyOS, in protocols, MACs, and routing, and all this stuff for in-building sensor networks. Now we can revert the usage. Because having this deployed, we can also use the radius of these telos nodes as sensors for frequency usage. And we have a beautiful distributed over 3 layers of the building platform for distributed sensing of the radio waves. And that is something which we use, and we enhance that by the mobile robots. So I'll show you 2 experiments. One is still with human. So what is the idea here? That a human being is walking, and the human carries a body area network on her body, is walking along this corridor, and we would like to know how many rooms, what is the space which is covered by interference just because somebody with a body area network walks across the hallway, with obviously different levels of power setting for the body area network. Funny enough, if we look at the empirical distribution of how many rooms are affected, it's obviously dependent on the level of signal, no doubt. But in general, you have a couple of rooms which are hit by the pure fact that somebody is walking there. So now you see the impact is pretty strong. The issue comes up. How would you like to do that? You could go for frequency hopping schemata. You could do some attempt for intelligent selection of the frequency you use. And we'll show that again as the setup for reversed situation. I'll now come in the building with my body area network. It will be a mock-up of a body area network by the robot. I will have my set of different devices radiating in the building, and I'll see how cooperation and sensing can enhance my efficiency in selecting proper channel, essentially that is the issue of a setup which allows studies of this type of strategies. So the idea is, again, we have our corridor. That is a mock-up of a body area network. So I have this robot. I have a broomstick. I have a transmitter and a receiver. So like something, say, on my shoulder and on my knee, imaginately. So that's not a very good avatar for a human being, but okay, it's the first mock-up. And that will be moving around here. Here I have the all measurement points which allow me to know what is going around, but not necessarily the guy will know it. So in one of these experiments, I'll show you the guy is simply statically running with a fixed channel. Predictively, not very good idea. And the other extreme is a cooperation using the connectivity brokerage architecture, where the sensing from the building sensors is giving some information to the body area network, kind of triggering his selection of frequencies. And that is, we have here two shimmer nodes. That is the twist boat, some controlled interference measurements. So that is the story. Okay, before I go to the video, that is kind of the information flow which we use here. We use the robot operating system for the robot. We use the Bern coordinator on the body area network. We have created a connectivity brokerage repository, a further development of what Arash started some time ago. And we have the possibility to feed that with the measurements and to exchange the data. So that is kind of the setup. I'll show you now two videos. Just a second. That was the previous one. That's not the right one. Sorry. The videos. So I'll show you two videos. So that's one with no sensing. Okay. So let me skip here. And so what do we see here? That is the view which the Kinect camera shows what the robot sees here in the corridor. That is a metric of a packet receive ratio between these two nodes on the mock-up body area network. And the robot will be traveling along the corridor. That is kind of like illustration of the frequency map. However, in the first setup, that is not known to the robot. The robot is just sticking to his channel 11. Should start moving anytime. I haven't clicked it. Yeah. So now it starts moving. You see the guy is moving over there. And obviously the packet success rate is decreasing when you come closer to the source of interference, and that is pretty lousy. So the guy has a real problem in communication running just through the building. And that is not a very high power source. That is just pretty continuously transmitting another sensor node. So it's not like Wlan, which would kill that in much bigger scope. Okay, so that is kind of the first experiment, and you have seen that goes pretty badly. Now it's a case where I supported by the infrastructure is showed here, and I have the map of the different channels. I'm scanning all the channels using my infrastructure. I make this information via repository available to this guy. And yes, he's able to select the channels depending on the position, and he's able to secure a pretty consistent, reasonably high packet success rate. By the way, this real, not the video, but the real demonstration of this setup got now the best demo award from the EWSN 2013 a month ago. Okay, So that is the story. Yeah, that's here is advertising. Sorry.
Have you tried it with like 5 robots at the same time?
Not yet, but we have them. So yeah, we could do. Absolutely good idea. Okay, so that leads me to the conclusion. The time is almost over. So what I wanted to transmit today in a shortest version. The first of all, that the usage of context, measured, established, computed, can significantly improve the networking efficiency and just reduce the billions which otherwise have to be thrown into infrastructure used in non-efficient way. Now, the issue is that gathering of the data which are needed to create the context is essentially a functionality which is conceptually best done if it's split between the application, the end systems, the connectivity provider, and the application services. So the question is, obviously privacy, I'll not discuss that here, but that's also the issue of understanding that each of the partners can gain something, and that's an issue of new economic business models. I'll not talk about that today. I'll elaborate on that more next week in my BWRC talk. And there's issue of new definition of the role of the provider, which cannot be just transporting, well, it is transporting of the bits, but the incentives for that cannot be volume measured. That's the absolutely wrong approach. That have to be tightly bound with real usage of the information, with what is the value of the information. And that needs completely different modus of cooperation between the players in the game. Okay, thank you a lot, and I'm available for discussion. By the way, I just wanted to do some advertising about 3 other issues which I didn't mention today, and namely which we follow, which might be interesting for the Swarm community. That is selection of servers to download the content with probing. There is ongoing work on predictive prediction of performance of massive crowd sensing applications using crowds as the measure, as a means of emulation of the crowdsource application. And then we have also interesting issue in benchmarking methodology for indoor localization. A new project started, but that's out of the scope of today. Thank you a lot.
Business model question quite open. And
yeah.
That seems to be kind of one of the big killers of the offloading kind of concept and stuff like that, right?
Okay, so I'll tell you what is my vision for that, and funny enough, the vision starts being now confirmed. So I have a lot of fun because the first time I came up with that 12 years ago, and nobody wanted to publish that. So eventually I used an invited paper to push it out, and I have a stamp on that. Otherwise I couldn't get it. And that was a claim that essentially we need what I called at that time dual charging, meaning the user is not paying for connectivity at all. The user is paying only to service provider for services. And service provider is paying for connectivity. That immediately creates for the service provider the incentives to reduce the amount of data. Immediately. Now, that is a beautiful push for technological progress, for differently structuring the applications. Now, 10 years, I haven't seen a lot about that. 2 years ago, the CTO of Telefonica in Spain made a very nice announcement saying, all these dumb Googles of this world have started to pay me for their traffic. They are making money and I'm making losses. So I loved very much this statement. In between, it popped up several times again. So it starts being multiplying. And interestingly enough, I think a month ago, people from Microsoft Research came up with a prototype showing that it's pretty well possible to do the accounting for such schemata. So there's a recent paper. I'll talk about that in my BWRC talk. But this reverting, so it's one step. Now, the second step for me is different definition of the roles. Today, your provider, you have a plan from AT&T, from Verizon, from whoever, and he considers himself your owner of your communication. And he's very envious. It's incredibly cares about not letting you use different networks, or you have to pay for roaming kind of incredible amount of money, which is rubbish. So number one, the guys do not understand that, for example, all the base stations are not necessarily collocated, and the efficiency would immediately increase if they would do seamless roaming internally. They shouldn't charge you. They should give you a bonus because they start making, they save money. They just save money. But no, they don't do that. Why? Very simple story. Because they are afraid they lose control over you as a customer. Now, the banking area has solved that many, many years ago. You have your bank, but you are allowed to draw money from almost every ATM, and mostly you don't have even a surcharge.
Pay $3 extra.
Well, not in Europe. In Europe, they have a banking union, and you have like thousands of ATM machines, which are in mutual roaming, if you like. And they are not envious. They know you need some unit whom you trust, who can manage your profiles and can do a lot of stuff for you, but not necessarily transport you over own networks. Broker, exactly broker, the best, the cheapest, the most efficient technology. And I'm absolutely sure it will come. India already has national roaming introduced since a couple of months. So it's a couple of movement. Yeah, but that's the key. I completely agree.
Just imagine a network of ATMs, none of which have any money in them. But there's no charge. Other questions? No? All right. Well, thank you again, Adam.
My pleasure. Thank you.